Morning everyone, I'm Claudia and I'm an Airbus sponsored NGD at the University of Bristol, and I'm going to talk to you about my research on forming of complex aerostructures. Aircraft production rates are set to ramp up significantly in the next decade. Wings will need to be faster, easier and cheaper to make and assemble. One way that OEMs like Airbus are looking to achieve this is by integrating primary wing structures to decrease assembly times. However, this leads to a more complex shape to manufacture. Another trend that we're seeing in aerospace is that jet engines are getting larger and larger to improve efficiency. This means that wings will have to be curvier to allow for ground clearance under a larger diameter engine. This adds to the problem of increasingly complex shaped structures. Aerospace is also investing in dry fiber processes due to their high deposition rates by comparison to current AFP technologies. However, this requires a preforming stage, which is currently a production bottleneck. Preforming is complex as it depends on a high number of variables and is currently still a very manual process with high variability. It can also produce wrinkles like the one you see in the picture with severe knockdown effects on your final component. In order to understand why these defects occur in full-scale components, several tests are carried out across the pyramid of scale, with the results from the two bottom tiers feeding into the top tier. However, this smooth transfer of knowledge up the pyramid doesn't always happen. In the bottom tiers, features and boundary conditions are not representative, and at the full scale, the data collected is often lacking and tends to be mostly qualitative over quantitative, making it difficult to compare results with smaller scale tests. This led to one of the main outcomes of my research, which was to produce a data-driven comparison across scales that can help de-risk the full-scale component. In lab conditions, the use of DIC cameras or laser line scanners are commonplace to scan wrinkles. This gives numerical data for preform quality. However, in a shop floor environment, these methods are not cost effective. On the other hand, taking photos of the preform quality is commonplace, and this is what we want to capitalize on. So let's say with a combination of good lighting and a high quality smartphone camera, technician A takes this picture that you see on the screen. The image is fed through an analysis tool that traces the boundary of the wrinkle and spits out numbers for the image, like wrinkle amplitude. And the data from all the plies is then collated into a plot like a defect frequency distribution. From this plot, manufacturing engineers can identify clearly which the problematic plies are and feed this back to design. The design engineers can then redefine the material formats, recalculate the orientation percentages for the structure, and redefine the engineering layer, which then feeds back into the manufacturer and some more data capture. Ultimately, this becomes a design for manufacture loop that has been enabled through untapping the potential of shop floor photos. The insights an OEM could get from having access to data like this are invaluable. And because this data approach does not rely on expensive kit like 3D scanners, it is compatible across the pyramid of scale. Thank you very much for listening.